welcome to 3.2 and 3.3. 3.2 is similar triangles and 3.3 is similar right triangles. So even though this might be a little longer than normal, we're going to go ahead and combine the two. They're very much alike. Okay, so just a review of what triangle ABC, similar to triangle XYZ, what does it mean? It means that if the triangles are similar, then angle A is congruent to X, B is congruent to Y, and C is congruent to Z, and then all the sides are proportionate to one another based on how they are written. So XY proportional to AB, and so on. So our first similarity postulate is angle-angle. This is the most basic of the similarity postulates for triangles, and it says if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Notice it does not prove that the two triangles are congruent because the sides could be very different lengths, but angle-angle proves similarity. So since it allows us to say two triangles are similar if only two pairs of corresponding angles are known to be congruent, because we know that if two are congruent, then automatically the third is as well. Another theorem is side-side-side similarity. So if the three sides of one triangle are proportional, okay, to the corresponding three sides of the other triangle, then the triangles are similar. So a little bit different than proving congruency, right? We're proving that two sides are proportional to the other three. Remember, we're checking all three. And likewise, we have the side angle side similarity theorem. So if two sides of one triangle are proportional to the corresponding two sides of the other, and the included angles between those sides are congruent, then the triangle is similar. So if we can't prove that the third side is proportional, then we would go to this theorem. And the similarity of triangles is an equivalence relation. Do we remember what equivalence relations are? Hopefully we remember that that means that the relation is reflexive, symmetric, and transitive, your three favorite words. Okay, so now we're moving into the next section of 13.3 that's talking about specifically right triangles. You're going to see that these are nearly identical to just any triangle, but we have a right angle in them instead. So an altitude drawn from a right angle to the hypotenuse of the right triangle separates the original triangle into two similar triangles, each of which is similar to the original triangle. It's a very cool thing how I feel like God created this. It has to do with the Pythagorean theorem, and it's the basis of trig ratios, which we'll learn hopefully in chapter 14, and if not, you'll get them soon enough in algebra 2. So here is a right triangle, and if I drop the altitude down from the right angle, which was angle B, and I drop that perpendicular down to the hypotenuse, I now have two right triangles that are both similar to the original ABC. So ADB is similar to ABC, and triangle BDC is also similar to triangle ABC. And therefore, right, there's my therefore, triangle ADB is also similar to triangle BDC. So this is very helpful when talking about setting up proportions and solving for sides. In the proportion A divided by X and X divided by B, the denominator of one ratio is the same as the numerator of the other ratio. And when this happens, x is called the geometric mean, which implies if I cross multiply, I will have x squared equals a times b. So I would have to take the square root. So for example, 8 is the geometric mean between 16 and 4, because 16 divided by 8 is the same as 8 divided by 4. Those two values are equal. So let's practice and find the geometric mean between 3 and 27. First, I'm going to set up a proportion letting x represent the geometric mean. So here I have 3 divided by x and x divided by 27. Now I'm going to cross multiply and take the square root of both sides. So we only take the positive value because with the negative, it ends up being the same. Okay, we select the principal root because the context demands for the result between 3 and 27, which cannot be a negative number. Okay, so let's just do one more. We're going to find the geometric mean between 6 and 9. So the same thing, we're going to set up the proportion, cross multiply, take the square root. Now here again we'll throw out the negative because the negative is not going to be between 6 and 9, but we do need to simplify the answer. Now the square root of 54 is going to give you a decimal on your calculator, and you need to know how to factor the 54 out. So the factors of 54 are 9 and 6. The square root of 9 is 3, right? And the square root of 6 can't be simplified any further because you just have square root of 2 and square root of 3. Neither one of those are perfect squares. So this is the part that you may struggle with, simplifying your radicals, but it is very important. You will lose points on a quiz or a test if you cannot simplify your radical. Alright, so let's just do one more because I have one that's not in the book. I just want to practice one more time. Setting up the proportion, cross multiply, taking the square root, and then simplifying our answer. Hopefully, if you have any questions about how I did that, that could be your question, but I think you can figure that one out if you factor out the 125. And if I needed to give a decimal answer, I could go from there. Okay, so the next theorem is in a right triangle, the altitude to the hypotenuse cuts the hypotenuse into two segments. The length of the altitude is the geometric mean between the lengths of the two segments of the hypotenuse. So again, this becomes very helpful when trying to solve for different pieces of a triangle. Now this proof is on page 550. It's awesome because it's only 3 steps. So I want you to look it over. I did not include it in the slideshow. But I do want to show you how this works. So if I set up my geometric mean where a divided by x and x divided by b, or I can go ahead and put these in terms of sides, similar sides. AB is to DB as DB is to BC. So if I know any of those measurements, hopefully at least 2 of them, I can solve for the rest. Okay, so in a right triangle, an altitude to the hypotenuse divides the hypotenuse into 2 segments such that the length of a leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to the leg. So this is a little bit different than the last theorem. Let's look at the difference. So I'm saying it divides the hypotenuse into 2 segments such that the length of the leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to the leg. So this is saying that segment AB is to AD, okay, as AD is to AC. So we're talking about the hypotenuse of the small triangle is to the leg of the large. And BC is to DC, so you have to find those on the triangle, as DC is to AC. So again, small is to big. Okay, so let's practice this. Given the measurements in the triangle HIJ, find x, y, and z. Okay, so that's a lot of missing information, but we have enough theorems here that we can figure this out. So let's start with x, because I feel like it's the easiest. When you're talking about the altitude, we know it's the geometric mean, so 4 is to x as x is to 16. We're going to cross multiply and take the square root, and we're going to take the positive root, again, because it's between 4 and 16, and we have 8. So now that we have that value, okay, so here I'm not using the values from x, because just in case I found the wrong value for x, I'm setting up a different geometric mean. Now how did I get the 20 there? 4 is to y as y is to 20, because I took the 4 plus the 16. That's the hypotenuse of HIJ. I'm going to cross multiply and take the square root, and I went ahead and simplified my square root because 16 comes out of 80, which the square root of 16 is 4. That leaves me with 5. Okay, so here's a good place to pause the video and see if you can do z by yourself, because I'm about to give you the steps. So why don't you go ahead and do that, push pause, and see if you can set up the geometric mean proportions to find z. Okay, here's what I have. Okay, 16 is to z as z is to 20. Again, 20 is the hypotenuse of HIJ. Cross multiply, and I simplified my radical. Hopefully you got the same answer as I got. Okay, because you have some practice problems now. Again, email them to me, and if you have questions, don't forget your questions. Some of you have been forgetting. Also, don't forget to email me and check your answers. Thank you, and see you in class.